across all the load. Unlike this is how it differs from diesel engine. Phi is going to be same, okay, but quantity is going to be different at different load. So because of the reason that we run close to 1.1 where you have high temperature, better flame stability, you end up in forming high HC emission, because as you know, when you move towards a rich region, you have an insufficient oxygen. Insufficient oxygen leads to partial oxidation of hydrocarbon. Partial oxidation of hydrocarbon leads to HC emission. On the other hand, when you move towards lean side, as you see below 0.8, you have a very high level of HC due to misfire. So few cycles, engine operating cycles will misfire because you cannot maintain a stable flame. So when the flame is not maintained, you don't have oxidation of hydrocarbon, fuel hydrocarbon, okay? So it will become unoxidized hydrocarbon that appear in the exhaust. Misfire cycle will lead to unoxidized hydrocarbon that appear in the exhaust gas. Okay, partial oxidation will also lead to several species, as we have discussed, that appears in the exhaust. So the takeaway here is SC can form with lean mixture due to poor flame stability and misfire. SC can form in rich mixture because of insufficient oxygen. So, and overall SC formation is governed by how the flow is happening in the boundaries of the engine combustion chamber. Okay, so we have different sources considering that. I've listed out those sources here along with the contribution of each source to the total HC formation. If you start with, in this case, crevice flow is one of the major source. You could see here that almost half of the total HC formation is through this crevice flow. We already discussed this crevice flow, if you recollect. So crevices are the dead volumes or dead pockets that are present in engine combustion chamber. One of the largest dead volume is between the piston top land and the cylinder liner. Piston top land and cylinder liner is one of the largest crevice. You could see that the piston top land typical size is around, vertical height is around 5 to 6 mm, and there is a radial clearance between the piston outer surface and the cylinder liner, which is less than 1 mm. So you have a radial clearance, and why do we have to have this radial clearance?
To avoid seizure during
to avoid piston seizure, because piston metal, you generally use an alloy. Based on the alloy composition, the thermal expansion is going to be different for the piston. So piston is subjected to high temperature. It undergoes thermal expansion based on the material that is used to construct. Nevertheless, whatever material you use to construct, piston is going to expand. To account for thermal expansion, you are giving this radial clearance. So what I want to convey here is you cannot avoid giving this radial clearance. If you don't give, when the piston expands, it's going to get stuck with the liner. That is called piston seizure, right? The piston cannot even move. You cannot run the engine. So to account for that, you have this radial clearance less than 1 mm. It's going to be different. It needs to be optimized. It cannot be too high or too low. Too high will lead to very high crevice flow, because as we understood now, it's one of the major sources for forming HC. So you need to carefully fix this radial clearance to reduce the flow of unburned mixture into this region. Once this is not only the dead pocket, there are other dead pockets around the intake and exhaust valve seats. There are uneven surfaces. So around the valve seats, you will have uneven surfaces. Although you measure it perfectly in the beginning, or a period of time when you run the engine, there will be unevenness in the surfaces, may not be even or uniform. So this unevenness will also create dead pockets. So mixture will go on, get trapped, and flame cannot enter in this region. Also, you have the cylinder head gaskets, cylinder head gasket between the head and the region and the piston. You have a gasket. Okay, so to seal the head perfectly. Okay, so you have this gasket, and this will also have some dead volume, wherein it allows the mixture, fuel or mixture, to go on get trapped. Spark plug electrode gap is another crevice volume. Spark plug threads. The region around the spark plug, you will have a lot of space, small volumes available. That volume is enough for the fuel to go and get occupied. And all these are very small volumes, dead volumes. Okay, and because of the small volume, the flame cannot go inside and burn the mixture that is getting trapped. Okay, this is the important point. the flame cannot move inside. We know that in SI engine, only flame should ignite the mixture, fuel or mixture. This region volumes are so small, but the surface is so high. So what I want to highlight here is in crevices, the surface to volume ratio is very high. Very small volume, surfaces are high. What will be the effect of high surface to volume ratio?
Higher heat loss.
Heat loss.
Heat loss will be high.
So heat loss will be high because of this. Since heat loss is high, the flame cannot go inside because the flame will get quenched. The flame cannot move inside because of very high heat loss. Considering high surface to volume ratio in crevices, the flame will get quenched. Okay, that is how the flame cannot enter and burn. The only option, whatever mixture trapped here, has to go back into combustion chamber to get oxidized. But if it has to go back, this flow, reverse flow or back flow from crevice region to the combustion chamber region, as you know, it is driven by the gradient, pressure gradient. And the pressure in the cylinder has to be considerably low, then only the flow, reverse flow or back flow can happen. And because of this happens during the very late expansion stroke, when the piston almost reaches VDC. During that point of time, the pressure in the cylinder is considerably low, and this mixture will start to move inside or flow back into the chamber. Since pressure and temperature during that period of time is very low, the fuel returning to the cylinder cannot burn. So what we can say here is that whatever mixture trapped in the crevices will miss the primary combustion. Primary combustion, it will miss because the flame do not have access. Since it misses primary combustion and go back into cylinder during later part of expansion stroke, where pressure and temperature are considerably low, this mixture cannot burn. Rather, it will oxidize slowly depending on the prevailing pressure and temperature condition. Based on the available pressure and temperature, the mixture that return back into the cylinder. Please note here that the mixture is ignitable because we generally prepare ignitable mixture. But the problem here is we don't have a flame during that period of time to ignite this mixture. So since the pressure and temperature are considerably high and there is no flame, based on the available conditions, okay, based on the available conditions, only slow oxidation or partial oxidation of these hydrocarbon can take place, and thus it becomes a source for HC. Since it is only partially oxidized during exhaust stroke, along with the exhaust gas, this hydrocarbon will go through the tailpipe and it is discharged into atmosphere as an unburnt emission. So this is one of the major contributing source for HC formation in spark ignited engine crevice flow of fuel air mixture. The second mechanism is flame wall quenching. It's very less, its contribution is very less, as you could see here, 5 to 10%. Nevertheless, we cannot ignore HC formation through this source. Flame wall quenching. Quenching means the flame get quenched. And this quenching happens when the flame goes near the wall. When the flame goes near the wall, what is happening in the wall region? You have a lower temperature. So you have a lower temperature in the wall region. So the flame will start to lose heat. So there is a heat loss happening when the flame moves closer to the wall. And if the heat released during the combustion period is less or equal to heat that is lost from the combustion region, the flame cannot survive. The flame is going to get quenched. So this is what is happening. Flame quenches at some distance away from the wall. It quenches at a finite distance away from a wall. Okay, so flame. So what we want to convey here is the flame cannot move all the way to the wall and get quenched. The flame is going to get quenched or extinguished at some distance away from the wall. And that distance is referred to as quench distance. As indicated here, this is the quench distance. So there is a finite quench distance that happens in a SI engine, and what will be the effect of this quench distance? Since flame cannot move all the way to the wall, there is some layer of fuel present in the wall. So you will have some fuel layer present here. Since the flame is quenched, this layer, fuel layer that is around the wall region, is not having any access to the flame, and thus it is not burnt. Since flame do not have access to this mixture, the mixture lying in the wall region is not burnt by the flame. Okay, and thus it can, so what will happen once the flame is quenched? You will have only burnt gases. There is no flame, but only burn gases. So the layer of fuel air mixture near the wall can only diffuse into these burn gases. Depending on the pressure and temperature of the burn gases, only slow oxidation or partial oxidation of this mixture can happen, but the mixture cannot burn or the mixture cannot undergo combustion. So you have a finite fuel air mixture near the wall region that is not burned by the flame, rather it is only oxidizing slowly depending on the temperature of the burn gases. Okay, this is what is the contribution from this source. Since flame cannot move all the way to the wall, there is some layer of fuel air mixture partially oxidize and contribute to HC emission. Now we need to analyze what will be the quench distance, what are the parameters that affect the quench distance. Where, as you know, when the quench distance is increased, you're going to have a high HC emission. But fortunately, this distance is generally small, okay, generally small. Because of this, its contribution is only 5 to 10%. So these are the variables. The type of fuel is going to affect the quench distance. For example, if you consider hydrogen, hydrogen flame can go very near to the wall compared to the hydrocarbon flame. Hydrocarbon flame in the sense gasoline or diesel flame will have a finite quench distance. Hydrogen flame quench distance is considerably less compared to the gasoline or diesel flame quench distance. Okay, so depending on the fuel type, the quench distance is going to be different. The other parameter is equivalence ratio. Equivalence ratio, for example, if you have a lean equivalence ratio, the temperature will be less, so quench distance may increase because of lower temperature. But if it is slightly rich, the equivalence ratio that results in higher temperature will reduce the quench distance. So quench distance is a function of equivalence ratio because it is varying the temperature, prevailing temperature. You know, based on the temperature, heat loss is going to be different. Pressure and temperature near the wall. If you have a high pressure and high temperature near the wall, the distance will be shortened. Okay, if the temperature and pressure are low, the distance will be high, SC will be high. Flame speed, when the flame moves at high RPM, I mean not RPM, velocity. When the flame less, this is what is happening with hydrogen kind of fuel. Hydrogen fuel has a very high flame velocity compared to the hydrocarbon fuel. That's why I say that the quench distance is shorter with the hydrogen kind of fuel. Geometry near the wall is also going to affect the quench distance because geometry is going to affect the surface to volume ratio near the wall. When surface to volume ratio is high, heat loss is high. So quench distance will be high because of this. Okay. So depending on the prevailing, geometry is going to be different, right, at different regions inside the combustion chamber. So if there are regions with very high surface to volume ratio, then the flame will quench at a higher distance, quench distance, compared to the region where the surface to volume ratio is narrow, lower. Okay. So these are the variables that affects the magnitude of quench distance. Based on the magnitude of quench distance, the HC level in the exhaust based on the contribution from this source is going to be different. The other source is adsorption and desorption in lubricating oil and carbon deposits. Typically 16% each from these sources, both carbon deposits and lube oil, contribute to around 16% each. So in total, it is 32%. It's high, so we cannot avoid adsorption and desorption. As we have already discussed, this adsorption and desorption are surface phenomena. It happens on the surface of the lube oil and surface of the carbon deposit. So what is happening when the flame moves, when the piston moves up during the compression stroke, it compresses fuel air mixture. And when the fuel air mixture is compressed, the partial pressure of the fuel is increasing, right? When the piston moves up, the total pressure increase and partial pressure of fuel also is high. Initially, the lube oil or carbon deposits do not have any fuel vapor in it, right? Since the partial pressure in the cylinder is high and lube oil or carbon deposits do not have any fuel in it, this is a driving mechanism for adsorption. So I'm just explaining how this adsorption in the oil or carbon deposit is happening. Carbon deposits are porous in nature. Okay, so you have space in between the deposits. That's why I say porous deposit. So because of this available space, the fuel will go and get trapped. Okay, because you have a high partial pressure of fuel in the cylinder compared to oil and carbon deposit region. And this difference in partial pressure is driving the flow of mixture, fuel mixture into either oil or in the carbon deposits. Okay, so and it is known that when fuel has high aromatics or olefins, so these are the components, hydrocarbon, that can create very high carbon deposits. Increased olefin or aromatic, you know, in SI engine, olefin and aromatic content are high. Okay, in order to increase antenna quality, we have a high olefin and high aromatic with gasoline. And these are known to form more carbon deposits in the engine cylinder. Okay. So there is a finite proportion of fuel and finite proportion of fuel that is going into oil layer as well as in the carbon deposits. This is what I mean by adsorption. So what is desorption?
Sir, reverse of adsorption, basically.
So it's a reverse process. So when do you expect this reverse process to happen?
When
Under the mechanism drives the reverse process. Okay, so we are talking about a flow back of fuel into combustion chamber.
So when partial pressures are very low and the
So
concentration.
inside the cylinder, when the fuel is burnt, when you have burnt gases, there is no fuel vapor in the burnt gases. Okay, so partial pressure of fuel in the burnt gas is 0. Okay, so this is the driving mechanism. So when the burnt gases go near to carbon deposits or oil layer, wherein they do not have any fuel vapor in it, so partial pressure is 0, and you have a fuel vapor present in carbon deposits and oil layer. This difference in pressure is driving the backflow. So there is a backflow of this trapped fuel vapor into the cylinder. That is, it is going into the burn gases, not it is going into the flame. So only with flame you can burn or combust this mixture. Since you have flame already quenched, only burn gases are present. Only in that period of time there is a backflow or reverse flow. Since you don't have a flame, the fuel vapor that diffuses into burn gases may get oxidized slowly. That oxidation rate is based on the pressure and temperature of the burn gas. Based on the prevailing pressure and temperature of the burn gas, the vapor that diffuses into burn gas is going to get oxidized slowly. So it's only oxidation, partial oxidation. It's not complete burning. That's why this is one of the source for SC emission. The next source is liquid fuel that is entering into cylinder. Ideally, you would expect only the gas phase fuel going into the engine cylinder along with air. As soon as you spray fuel through a powered fuel injector, we expect that the sprayed fuel get into gas phase immediately because gasoline is a volatile fuel. Right? We expect that the liquid phase gasoline is converted to gas phase and carried away into the cylinder through the air. Okay, air stream will carry this gas into fuel gas into or vapor into cylinder. This is an ideal case, but actually what is happening, some liquid fuel are also carried into the engine cylinder. Okay, especially under acceleration or any transient condition, you have very little time for vaporization. So under those conditions, the liquid phase fuel getting into the cylinder is going to be high. You will have a high proportion of liquid phase fuel that get into cylinder, especially the heavy fuel, right? So we know gasoline has a, what is the boiling range of gasoline? Hello?
So 40 degrees.
25 degrees.
40 degree.
Minus 25 degrees.
Minus 25 degree. Boiling range.
Sir, 160 around.
Sir, from 20 degree to around 200 degrees.
Yeah. So these things we discussed in chapter 1. So you should always remember what we discussed early, because we are carrying that for our analysis here, right? So you should not forget the previous chapter, whatever we discussed about combustion and about fuel, because they are important to know to analyze the pollutant here. Okay, so we are analyzing how the pollutants are formed. So the concepts that we have discussed about the combustion event, about the fuel, that are important to recollect, because we are using those to analyze this pollutant formation. Gasoline boiling range is 20 to 200 degrees Celsius. So you have a multi-component mixture with a wide boiling range. The heavier hydrocarbon, you can think about this heavier hydrocarbon, they will stay in the liquid phase for a longer period of time. Okay, above 100 degrees Celsius to 200 degrees Celsius, they are heavier hydrocarbon. They are going to stay back in the liquid phase for longer period of time. So what you can expect, especially under transient condition, where you have very little time for engine warm up, engine is in a cold condition, you would expect a considerable fraction of liquid fuel entering into engine cylinder. If at all liquid phase fuel goes into engine cylinder, what effect it will create? It's going to vaporize slowly, because when the piston, initially it will be carried with the air stream, liquid particle. Okay, when the piston moves up, compresses, it's going to slowly raise the pressure and temperature. The mixture is going to vaporize. Liquid phase is going to get into gas phase. But because of this liquid fuel entry, what do you think will happen in terms of SC emission?
It will increase.
It will increase.
Yeah, it is going to increase. Its contribution is 20%. What will be the mechanism that will drive this SC formation with liquid fuel entry?
Sir, there will be an heterogeneous mixture which will not completely burn the fuel.
So you will have gas phase and liquid phase, and kind of non-uniform mixture distribution. You are saying that will happen. The mechanism is when you have a liquid phase, this adsorption, whatever we discuss, it's going to be very high, right? Adsorption of gas phase and liquid phase. Liquid phase can easily adsorb into lube oil. Okay. And here you should also note that this adsorption rate is a function of lube oil thickness.